strengthened by the grain size reductions. Okay, so I have already discussed what the kind of the grain boundary, grain size and grain boundary defects. Okay, so here is example first one, how you can strength, provide the strength to your uh, material. The size of the grain or the average grain diameter in a crystalline metal influences the mechanical properties. Obvious, the mechanical properties behavior will affected by which the way your grain size is there and your grain size diameter is there. Okay, that in your polycrystalline metal it is most important and that will basically define your mechanical properties. Okay, so adjacent grain normally have the different crystallographic orientation and of course the common grain boundaries as shown in the figure. Figure is here. See here. See. So this is the grain boundary, right? This is the grain boundary. This is the grain boundary. This is the grain boundary. Okay. But you can say this is a slip plane. The movement of your dislocation is moving in this way. How? As you can see here, this is your dislocation. This dislocation is dislocation. You can here this see, right? Everything is perfect here. Everything is perfect here, but this dislocation is present due to which here at the top you would have the compressive nature and at the bottom you have the tensile nature, right? And this is your boundary. So as you can see here, right? So why it is a boundary imperfection? Because at the boundary you have not perfectly aligned atoms. As you can see, there is no perfection. There is no perfection. There is no perfection. There is no perfection. Okay, this is not your boundary line. This is your kind of dislocation slip plane. That's why it is indicated here. So slip plane is a different kind of things. But here the grain boundary is only this one. This one the grain boundary. So there are the two kind of the grain boundary, the two kind of the grain here in this particular example, grain A and grain B. Okay. So in a grain A, there is the slip plane or the dislocation, edge dislocation, which is present here, that is moving from left to right. Okay. Yeah, or you can say from A to B, right? So there is an imperfection at, you can see here, there are two kinds of the imperfection here. First one is the boundary imperfection and second one is your edge dislocations. Okay. So during the plastic deformation, here you can see, during the plastic deformation, slip or dislocation motion must take place across this common boundary. Obviously, the movement of the slip is going to be end at the boundary, right? Say from the grain A to B, the figure below, the grain boundary act as the barrier to dislocation motion for two reasons. See here. The movement of dislocation or dislocation coming from, suppose from here. And at the end, they are reaching at this boundary. Boundary is here. This is, as you can see, this is your grain boundary. This, this is your grain boundary, right? So once the dislocation reached at this boundary, what happened? They will stop further moving from B toward the B because there is a barrier. There is the stoppage, there is a barrier. They cannot move further. And why they stop? There are two reasons. Because the two grain are of the different orientation, dislocation passes into the grain B must changes its this direction of the motion. This becomes more difficult as the crystallographic uh, misorientation increases, right? What does it mean? It means, as you can see, they are perfectly aligned as horizontally, but they are little bit little bit tilted, right? They are at some angle. It means if they want to move in the same way, either they have to tilt in this way, in that way, right? And that is required more ability or more energy that they don't have, right? So for their own movement, the the alignment must be like this, in this way, straight as they were moving from earlier, right? So if they are in that fashion, they will move further. But here, as you can see here, they are tilted little bit. It means they cannot move, they will stop at that particular boundary. Okay. Second one, what the second reason is, the atomic disorder within the grain boundary region result in the discontinuity of slip plane from one grain to into the another grains. Obviously, okay. So disorder within the grain boundary, even inside the grain boundary, there is some kind of the disorderness that will not allow the uh, 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 the imperfection or dislocation to move further. So that will stop here. Okay. So for the high angle grain boundaries, it may not be case that the dislocation uh, travels grain boundaries during the deformation rather than dislocation tend to pile up. Pile up means they will, collected here. The all dislocation will come at the boundary, okay, and they will stock here at that particular. They will, sit here. So it's a collection kind of. Whenever, I mean, if suppose the second, this is your first dislocation, suppose here some other dislocation is coming from here, they all will come up and end here. It means they all will combine together and they will pile up. They will have the storage here, you can say, at the boundary. If the same, if this dislocation is coming from here, in the case of this grain boundary or grain size of the B, they all will come at the boundary and will sit here. It means the boundary will act as a storage where the all the kind of your dislocation will sit. Okay, and they all will be here. Okay, so this is the your pile up. Pile up means the backup. So they all will have sit here at their boundary, at the grain boundary. The pileups introduce stress concentration ahead of their slip planes, which generates a new dislocation in adjacent plane. What does it mean? They will act as a the stress concentration. Stress concentration means the area where the stress is very high. Okay, so that is known as your stress concentrations. Okay, so that will generate the dislocation in a nearby the grain size. Okay, suppose I mean the only in the egg grain there's a dislocation and they are moving and they are moved and come at the boundary. Now they have sit, and due to the collection of many dislocation here, they have the more stress concentration, and that will enhance and that can generate the new dislocation in nearby grain. So if they have come from A and B, now that would be not of the same kind. Okay, there could be any means there kind of there would be any kind of the your dislocation, but that would be generated in that nearby grain. So that will basically somehow disturb your nearby grains. Okay. So a fine grain materials, one that has a small grain, is harder and stronger than one that is the coarse grain. So what is the? I mean, there are many kinds of the grains. Fine grains, coarse grain. Okay, fine means they are very small. Okay, and coarse grain means they are little bit bigger than of that particular one. Okay, because the former one has the greater total grain boundary area to impede dislocation motion. For the many materials, the yield strength, which is the sigma y, varies with the grain size according. So how the sigma y means the yield strength. That yield strength will depend on your grain size. How? This is the equation. Sigma y is equal to sigma naught plus ky d to the power d root, basically 1 to a half means d root, but minus means 1 by. Okay, this is your equations. Okay, so this equation is known as Hall-Petch equations. His name is d is always the average grain diameter. I mean the grain of the of many diameters. So average of that grain size is known as your average diameters. Okay, sigma naught, what sigma naught is and give either just a constant. Okay, that is belongs to your material. Okay, the above equation is not valid for both the very large cores and extremely fine grain crystal and crystal. Means if the grain is of medium size, then you can apply only these particular equations. Okay, to have an idea what the kind of the yield strength is there on the basis of their grain diameters. Okay, but if the grain size is very high or very low, I mean you can say the very high means they are very bulky nature, and if very small means very fine, then you cannot have the perfect decision, or you cannot basically apply these particular equations. Okay, what equation? The Hall-Petch equations. Okay, so this was the first year strengthened, I mean, by grain size reductions. Okay,